Okay, so in this video I'd like to go over an example of a gabled frame, or a frame with inclined members, where we use the matrix vector kind of approach, where we form AF and PF minus PFW by hand, all right, using compatibility and external work. All right. So this is a very tedious process when we have inclined members. So I just wanted to kind of give you the basics of how to do it. And then when you do your programming assignment for general plane frame analysis, a lot of this stuff will be handled by matrix vector transformations and assembly inside a loop. Okay. Okay, so this is the frame model. All right, so there's a 10 kip load applied here at node 2. There's a support settlement down here of 0.05 feet. And then there's member loads applied in the global direction up here. Okay, there's 11 unconstrained degrees of freedom. Okay, and then there's also 4 constrained degrees of freedom. All right, shown down here at the pin supports. All right, and then all members have the same EA and I. Okay. So down here, just a summary of the element geometry. Okay, so recall that delta x is just the xj minus xi, x coordinates at the j and I coordinate nodes, sorry. And then delta y is that. Okay, L is the square root of delta x squared plus delta y squared. All right, and then cosine is delta x over L, and sine is delta y over L. Okay, so a lot of this information could be useful for doing your programming assignment. All right, if you analyze this frame using assembly loops, all right, and you want to check the geometry of the elements and your transformation matrices, this is all useful information. Okay. So without getting into too much detail, some of the other PDFs posted on Canvas get into these derivations, but for element 2, we can resolve that 1 kip per foot global distributed load into a longitudinal component of 0.48 kips per foot, negative because it's going from J to I, all right, or along the negative x-axis. All right, and then the transverse distributed load that would come out of that 1 kip per foot distributed load at the global level would be 0.64 kips per foot. Okay, and then down here, when we do the external work calculations, we need to turn those distributed loads into resultants. All right, and that'll look something about like this. All right, so we have an axial resultant at the I end of 4.8 kips. All right, and then a transverse resultant of 6.4 kips. All right, go in there. Okay. So again, I'm not going to go into details on where those really came from, but we'll use them for the calculations. And again, I'll just kind of show you how tedious some of this stuff is. All right, with inclined members. All right. So then for element 3, all right, it has, when we resolve the global distributed load of 1 kip per foot onto the longitudinal and transverse axes of the element, we get something like this. 0.2 kips per foot transverse along the negative y-axis for the element, and then 0.4 kips per foot along the positive direction. Okay, and then its resultants, or those resultants, would look something about like this: 5.366 kips, and then negative 2.683 kips down here. Okay. All right, and that transverse resultant's acting at the center, or the midpoint of the element length. Okay. And this might be a typo. All right. But at any rate, we have those loads. We'll come back to those, but we'll use these values here and here to get the PB0 for the elements 2 and 3. All right, and then we'll use these two cases here to help us get PF minus PFW. All right, so just like before with our more simple structures, right, we can form the block diagonal basic stiffness matrix from element properties, using E, A, I, and L for each element. We get these values, or this block diagonal matrix here. It's 12 by 12. There's 4 frame elements, and each frame element has 3 basic degrees of freedom. So this is for element 1, this is for element 2, element 3, element 4. Okay. Pretty much all off the shelf, easy stuff. All right. Then we can form the fixed end basic forces. All right. So this is for element 1. There's no element or distributed loads. Element 2 has distributed loads. Element 3 has distributed loads, and then element 4 has no distributed loads. All right. But for element 2, we had Wx equals negative 0.48 kips per foot. Wy equals negative 0.64 kips per foot. All right, so this 2.4 is negative Wx L over 2. All right, so negative gives you a positive. And then these two right here are minus and plus Wy L squared over 12. Okay, so again, this is Wy is negative, right? So you get some double negatives, right? Okay, and then for element 3, we have Wx equals positive 0.4 kips per foot, and Wy is negative 0.2 kips per foot. All right, so then, applying these formulas here onto this little block, we get those values shown right there. Okay. Let me erase some of this stuff. Okay, so now we can go in and form the compatibility matrix A sub f and the equivalent nodal load vector PF minus PFW for each of our compatibility states. Okay, and then there's a lot of typos in this sentence up here, but this should be compatibility. All right, and this should say measuring. Okay. All right. But for the first unconstrained degree of freedom, I believe we'll come back to the result up here, but for unconstrained degree of freedom number 1, that's moving this joint over a unit amount. All right. And then holding everything else fixed. And we get a deflected shape that looks something about like that. Okay? And then the chord for each element, elements 3 and 4 don't move. Oops, sorry. Okay, so we get that. Okay, so UB for element 3 is all zeros. UB for element 4 is all zeros. Okay, and then UB for element 1, I believe this is 12 feet long. All right, so we have no axial, and then from chord to tangent, 1 over 12, 1 over 12. All right, for element 1, and then for element 2, it gets kind of complicated, but we're going to have a non-zero value for each one of those. All right, element 2 is shortening, and then it's also, there's some rotation of the tangent relative to the chord. All right. Sorry, that wasn't 12 feet. This column is 10 feet long. Okay, 1 over 10, 1 over 10. Okay, but we get down to this column of A sub f. This is for element 1, this is for element 2, 3, and 4. Okay, but you see here, this is all the geometry. We can at least reason through the signs, right? Like they're all negative, right? So this element 2 right here is shortening, All right, so the first entry will be less than 0. And then the rotation from chord to tangent is clockwise for both. All right, so those will also be negative. Okay, I don't want to get into the details of those calculations. All right. Okay, now to get the PF minus PFW entry, we have to look at the work done by all the nodal loads, right? So we have our 10 kip load applied here. Right. Then we also have our resultants from the distributed loads applied at the appropriate places. All right, so 4.8 kips at the I end of element 2, and then 6.4 kips transverse at the center of element 2. And then for element 3, we're going to have 5.366 kips at the I end, and then 2.683 kips at the center transverse of the element. Okay. All right, so we need to figure out the work done by all of these loads going through the displaced shape of compatibility state 1. All right, so again, we move this over a unit amount. Doesn't really matter what the what the deformed shape looks like. We just really need the chords and how they move. All right, but we need to get all the external work. All right, and this is where things get pretty complicated, and I don't want to go into too much detail here. All right, but work external, I think it's pretty easy to get 10 times 1. All right, then we're going to have x component of this force opposing the 1 displacement here. So we're going to get a negative contribution from the 4.8 kip load. It has an x component going the opposite direction of the displacement, so that's that. All right, and then we also have this point where the resultant transverse load is applied, and this is moving over an amount here. These vectors are not collinear, right? So we need to resolve this 0.5 into that or that. It gets really complex, all right? And again, I don't really want to go through it, all right? But these two loads are not moving. But you get 1, 2, 3 contributions to the first entry of PF minus PFW, okay? And those are shown down here. So there's the 10 times 1 we talked about. There's the axial resultant, the 4.8. All right, it has a component of 0.8 on there. And then the 6.4 times 0.3 is the work done by this load going through this displacement, the dot product of this vector with that vector. All right. Complicated, right? Okay, so that's the first degree of freedom. All right, we can do also the 5th unconstrained degrees of freedom, which is the vertical motion of this joint right here. So we'll get the chords, we'll get that. This gets really, really dull. This is why we have computers to do this stuff, right? But that would be 10 kips. We'd have 4.8 kips here. We'd have 6.4 kips here, and 5.366 kips here, and 2.683 kips here. Okay, so there's no work done by these loads. All right, this point's not moving, but this point's moving from here to here. All right, so dot product of this with that. All right, and then the dot product of this vector with the one vector there. All right, and then the dot product of this vector with that vector will give us the external work. All right, and then we can get the element deformations, all right, from the extension of this element 2, and element 3, they're both going into tension, so they're going to have positive values for their first entry in UB. And then element 2 has some negative rotations from chord to tangent, and element 3 has some positive rotations from chord to tangent. Okay. And you see that down here. All right, this is element 1, element 2, which we said was extending, all right, and it had negative rotations from chord to tangent. Element 4 is all zeros, and then element 3 we said was extending and then had positive rotations from chord to tangent. Okay, and then here's all of the entries or contributions, excuse me, to the external work. All right, the fifth entry of PF minus PFW. All right, it's painful. All right, okay, rotational degrees of freedom. I think I'll skip that. Those are pretty easy. All right, you just get all zeros and ones for your compatibility, and then the external work is usually all zeros for that. But you'll get down to a compatibility matrix that looks like this: 5, 6, 7, 8, 9, 10, 11. So when you're doing your programming assignment, you're not going to explicitly form this matrix. All right, it's just this is more of a module 4 kind of thing. All right, but at any rate. And then here's the entries of PF minus PFW, all the external work calculations: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, but what's of interest is the stiffness matrix. You can carry out this triple product, AF transpose KB AF, and you'll get this 11 by 11 stiffness matrix. And you can use this to check or spot check your module 5 assignment. If you enter the input for this gabled frame, all right, your assembly loop should form this stiffness matrix. Okay, you see where the zeros are, you see the diagonals, you see the off diagonals. Okay, so this is good for verification. All right. Okay. And then the constrained degrees of freedom at the pin supports. All right, so this is element 1, 2, 3, 4, and then this is degree of freedom -1, -2, -3, -4. Okay, again, you won't form this explicitly in module 5, but it's just there for completeness. All right. There's PCW, it's all zeros, all right. And then the effects of support displacements, the UBC, is shown here as element 1, element 2, element 3, element 4. And you'll see that there's a non-zero entry for element 4, all right. So as this support moves down 0.5 and this part up here stays put, that's just stretching this element out. All right, this element over here goes into tension, right? Extends or changes in length by 0.05 feet. All right, so that's why that's a positive 0.5 right there. Okay, even though globally this is acting downward, you might think that's negative. All right, but it's extending the element. All right, so at the element level it becomes positive. All right, but this is what the the UBC vectors would be for each element. Okay. And then when you take all the effects of nodal loads and member loads, the whole right-hand side vector that you'll assemble, all right, through your element loops is shown here. All right, so this again is good for spot checking your module 5 assignment. When you get down to the end of the loop before you solve for UF, this should be your total right-hand side vector. Okay, and you see this very large entry right here is from the support displacement. Okay, or it's due to the support displacement. Okay, then you solve. This is our system of equilibrium equations. You'll solve for U sub F, right? And you should get these 11 entries. Okay. You can recover basic forces, right? This is element 1, 2, 3, and 4. Okay. And then the reactions you should get are shown here. But again, you won't do it this way. You'll use assembly to get the reactions. This is the matrix vector expression for the reactions. All right, but that does not scale well, and it's not efficient for larger structural models. But you can use the assembly, kind of the second assembly loop in your assignment number 5 to get these reactions here. All right. Okay. So again, this is showing how to do frame analysis with the module 4 approach, where you have big matrices and vectors at the structural level, but that does not scale well to a larger structure. All right. But the objective here was to show you, or to give you, a good test case to help make sure that your module 5 assignment, where you do assembly with lookup vectors and loops in your Python programs, gives you a good test case to make sure it's doing everything properly.